Okay, so the topic for today, we are again going to be talking about angular momentum. So angular momentum and then rotational kinetic energy. So this rotational kinetic energy here, I think there might be one more term here. Yep, rotational kinetic energy. Okay. So we're also going to be talking a little bit about doing like a torque statics problem today. But before we get started, so I introed some stuff last time about torque. So we have our basically how to calculate the mass moment of inertia, the mass of the object and how it's distributed and how that resists rotation. So like how much inertia it takes to get an object spinning or how much inertia it has when you're trying to basically slow it down. Its resistance to change of movement is all part of this mass moment of inertia term right here. Okay, that mass moment of inertia affects how quickly, or the rotational kinetic energy of that object. So the energy that the object has while it's spinning has a lot to do with that I term, very similar to when we deal with mass with an object that's moving in a straight line, right? So if I have something that has like a lot of force, right? Or I have, okay, I have a really massive object, right? And I'm applying a force. If I get it moving, I can't get it moving if I apply the same force to a really massive object as I apply to a really small object. So say I have like a really small block and a really big block, and the force that I apply to both of them is the same, right? This object is going to be able to accelerate faster, right? Or yeah. So if I have the same force, so I have force is equal mass times acceleration. So my force, right, ma. So basically my force over mass, I'm going to have a larger acceleration with this smaller block, right? Than I'm going to have with this larger block, this big M, right? So I can get it moving faster, right, with a smaller mass, but it's going to be easier for me to stop it also, right? It's going to have less inertia. Same thing with these rotating objects where it's dependent on this mass moment of inertia. Okay, so just kind of a little overview. Maybe I'll leave that there. Okay, so yeah, so like a little m is going to be bigger than a big M, but it's going to be harder to stop that a big M, right? Because it has more mass. Okay. So we also talked a little bit about torque. So torque is we often see it represented too as RF sine of theta. Okay. But we want to note it's also a cross product, right? When something is a cross product, it follows the right-hand rule. What the right-hand rule means, if I have two vectors, if I have my r vector, for example, and then I have my force vector. Let me see if I can find them on here. So this is my r vector. Okay, so let me highlight this guy. So my r vector, right? And then my force vector. What I want to do when I take my cross product is I am going to lay my pinky finger along the direction of this first vector, right? This r vector. And so my wrist is kind of like at the nexus where these two points meet. So pinky finger, and then I'm sweeping my hand to F, and then my thumb is going to be in the direction of the torque. So in this case, the torque is actually would be acting into the page for this particular problem. So what the right-hand rule tells us, or when we do any kind of a cross product, is basically that the resulting vector is perpendicular. So if this is some angle, right, it's going to be perpendicular to the plane that those first two vectors are in, and the direction, if it's kind of like into or out of the page, depends on that right-hand rule. Okay, so just kind of a little bit of an overview there. We'll talk a little bit more about that. We'll see a few problems where we kind of deal with the direction of torque today. Okay. Then we talked a little bit about rotational dynamics. We talked about a really, really important concept that if an object is rotating and moving in space, it has translational kinetic energy, and it also has rotational kinetic energy. So like we see here, maybe I'll leave that yellow in there too. Like we see here, so this is the translational kinetic energy, which means the kinetic energy to get it like moving, you know, like in say the X or the Y direction. And then the rotational kinetic energy is the energy that it has while it's rotating, right? If this is just some object that it's been, you know, kind of rotating, this would kind of be a point on the outside line or whatever. So this is not the most descriptive line, but and then the rotational kinetic energy is the kinetic energy that it has while it's rotating, right, as it's moving down. Okay. Then we talked about kind of work done by torque, and how your work done by torque, we can either measure it as the change in rotational kinetic energy. I think we did one problem where we had a block that was spinning and then we pulled it kind of through the middle, and we looked at the change. We can also look at power, which is going to be the angular velocity multiplied by torque. And work can also be measured as the torque times the change in angle. Okay. All right. And then we have angular momentum. There's some concepts that I want to kind of bring up about angular momentum today just before we get started. And I think that right here is kind of like a good intro. So I want to kind of explain what these equations mean. So this is angular momentum of like a particle, right? Just like one single particle, which can be modeled as like a point mass. And this is the angular momentum when we have an object that has like a mass moment of inertia. So let's kind of talk about what that means and like how torque would change your angular momentum and like what that looks like. So like if we apply a torque to a figure, how can we tell if it changes its angular momentum or not? We're going to do some problems where we can see that. We also did one problem last time, but let's kind of talk a little bit about that. So we know that torque can be modeled as the change in angular momentum, but it actually depends on where that torque is acting, okay? So I'm going to draw two different things because we're going to see a lot of angular momentum of a point object type of problems. I think we did one last time, but we're going to be using this kind of a lot today. Okay, so if I have a point object, right, and so this is just some point mass, right? I'm modeling it as a point mass. And the mass moment of inertia for a point object is 1/2 mr squared. Okay, I have some point mass, and it's rotating around a circle. Okay, so this is the one where I can have, so my L is equal to R cross P. This point mass has some linear momentum, right? P, which is a vector, and then I have a distance R, right? And I'm going to end up with a torque, right? Because of the rotation of this object, right? Okay, and I want to know like what my torque is going to be. In this case, we have the torque. So fingers along R cross to P. I do this the right way? Yeah, okay. So L is equal to R cross P here. And this is my cross product with direction, and the right-hand rule applies, right? Then I also have these extended objects where I have like a, like for example, like a sphere, etc. And I can use both equations for the extended object and for the point mass. And I'll kind of show you how they'll end up interchangeable here. But so this one also is, so I have L is equal to I cross W, okay? And like we talked about before with the cross product, if we're given like two vectors for I, or sorry, not for I, if we're given a vector for W, we can also figure that one out as well. So this is actually just multiplied, sorry to confuse you guys. Okay, so this is angular momentum. Okay, so how would the torque be able to change an object? Torque, as we saw, is the change in angular momentum over time, okay? So it's what causes something to spin, right? If we apply a torque, we want to look at like a moment arm and think about what direction that torque is causing it to rotate, clockwise or counterclockwise, right? So I can rewrite this little piece up here. I know that I'm going to write, torque is equal to delta L over delta T. So I can say torque times my change in time is going to be equal to my change in angular momentum here. Okay. So say, for example, I have some random torque, okay? And I want to think about if I apply a force to create a torque, right? I know that my force is going to be equal to, right? Force is equal to R sine, or sorry, force, torque. Torque is equal to RF sine of theta. Sorry, it's also early in the morning for me as well. So I want to look at my angle between, right, for theta, it's the angle between this R and the force, right? And then I want to see if this is going to create any torque. Well, that force would be acting to change the the radius, right, for this guy. So my radius, like my initial radius, right? Initial radius would be smaller than the final radius because this thing would like be smaller, right? The radius would be smaller. And my angular momentum would be conserved, Li equals Lf. But I wouldn't see change in angular momentum, right? This is not enough to create a torque. If I create a torque in the system, that angular momentum is not conserved because I'm adding an additional force. So I could use it in a conservation of energy equation, but I can't assume that my initial and my final torque or my initial and my final angular momentum are going to be equal. I would have to add that additional term, right? I would have to add this change in angular momentum. I can't just say the initial is equal to the final if I apply a force. So I kind of have to think about what that force does to a system, right? So what if I apply a force? So in this case, so this wouldn't change, right? This would be, so I would be adding no torque based on where this force is. So this force would not add any torque. So there's no torque. Okay. So torque wouldn't exist. I would be doing work by applying that force, right? I would be moving the object in, but my angular momentum would be conserved. What about if I apply a force here? Maybe I'll use a different color. What if I apply a force on the edge here? If I apply a force on the edge, right? What about that? In that case, I would have a torque, right? My torque, right? I would have R F sine of 90 degrees, right? I would be causing rotation. I would be adding to that rotation. I would be adding to that angular momentum. I would have, a torque and over a change in time here. So I would be causing a change in angular momentum. So I would cause a change in the angular momentum of my system. And so in those questions where they say, is it conserved based on where you're applying that force? The answer in that case would be no, because we are applying an external force that would change it. Okay, so this is kind of a tricky concept, and I think it makes more sense if you see it in problems, but I just kind of want to point out what it is and what we're talking about here before we get into the problems. Don't just take this at face value, look at the examples, because if you just look at this, I think that it will cause confusion if you don't actually go through the problems, because there's ways that we deal with these cases. These are not general rules. The problem isn't unsolvable. You just have to take it into account, and it'll just kind of help you answer basically a multiple choice part of a question like this. Okay, so this was, again, my walkthrough just kind of on some of the general equations that we're going to be using today and on some of the concepts that we touched on last time. Now we're going to get into a few more examples for today.